So a few years ago, I interviewed Alan Rohner, the CTO and co-founder of Griffin Bank, for our Closure In series. And he talked about their technical stack, how they had built a banking platform from scratch. And he also talked about how Foundation DB was one of their key pieces of technology. It was at the heart of their platform. And the reason that it was so effective is that the Foundation DB team had pioneered new methods of testing and verification of software. They'd pioneered deterministic simulation testing. And they'd kind of focused on the testing problem first and built the database later. And actually, the XTDB team has been using these deterministic simulation testing techniques this year to verify the correctness of XTDB. The team behind Foundation DB went on to take those testing techniques and that pioneering work to verify distributed systems at scale and have built a new platform, Antithesis. And this is a platform for autonomous verification of software systems. Now, Antithesis was founded in 2018, so they probably didn't know that verifying the suspect code that we're producing and finding new ways to unlock this kind of verification bottleneck would be such a hot topic in 2026. So here to tell us more about the effective ways to verify your code when working with agentic tools is principal engineer from Antithesis, River Keefer.
Thank you for the introduction. Really happy to be here. What you said is absolutely true. We're feeling hugely lucky that everyone is so interested in software testing all of a sudden. That was not intentional. So yeah, I work on the research team. We do simulation testing of distributed systems, but that's not what I'm going to talk about today exactly. I don't think I need to convince this audience that LLMs are fundamentally unreliable tools in some sense. They're statistical machines. This isn't to say that they don't sometimes give you, and even often give you useful and correct output. It's just to say that they don't always give you correct output in the context of programming. And thank you, Nick, for pointing out lots of ways in which that's true. I think of myself as a systems programmer. My background is in compilers. And when you're working on that kind of infrastructural software, the cost of a mistake can really be quite high. So it's common for people in that world to have this reaction of, well, these things are unreliable, therefore they can't be useful. And that was my reaction for a long time. But we know from history that it's possible to build reliable systems from unreliable components. Here are some examples, both from computing and from nature. Things like error correction, computer networks, TCP/IP, consensus protocols. It's funny, I'm not a distributed systems expert, but I do deal with them all the time at work. And distributed systems are all about this. They're all about taking fundamentally unreliable pieces, nodes that you don't trust, computer networks that you don't trust, and building a system that behaves reliably as a whole on top of that. And yet it took me a really long time to accept that maybe this is possible to do also with large language model output. Yeah, worrying about correctness is not new. We've been worrying about correctness pretty much since we got computers. This is Dijkstra advocating for formal verification in the 1970s. He says, today the usual technique, or a usual technique, is to make a program and then to test it. Program testing can be a very effective way to show the presence of bugs, but it is hopelessly inadequate for showing their absence. The only effective way to raise the confidence level of a program significantly is to give a convincing proof of its correctness. Now, I'm aware this is quite a hardline position. But I think lots of people are sort of appreciating this now, and formal verification is also all of a sudden getting lots of attention. I think these techniques are very interesting, and they deserve the attention. But I also think that they're not yet equipped to deal with much of the messiness of real-world systems. I spent a bit more than a year in academic computer science working with interactive theorem provers, and those tools are incredibly powerful, but they're also incredibly difficult and labor-intensive to use. So today I'm not going to talk about any of that stuff. I'm not going to talk about deductive verification or model checking or symbolic execution. Instead, I want to tell you about a testing methodology that I think has the most hope of taming the output of these things, and that is property-based testing. So the argument that I want to make is that perhaps property-based testing, which I will refer to from now on as PBT, can function as a kind of error correction for coding agents. So I'm not going to assume that people have seen PBT before, so I'll give you a bit of an introduction. To explain PBT, I'll start with traditional testing and then explain how PBT is different. So imagine we are testing some kind of user registration system. This is like a fairly typical unit test written in Python. We've got some registry object with a cap on the number of users, and we're adding users to that system, checking that the registration went through, and then we're adding a subsequent user and making sure that the registration was successfully closed. So yeah, just checking that the user cap is behaving correctly, essentially. This test tells a story, and people like thinking in stories. The story of this test is that we can add users up to the cap, and then once we've hit the cap, that registration closes. That tells us something very important about our system. But this test is falsely general. Think about the name that a typical engineer would give to a test like this. It would probably read something like, can add users up to limit. That's a very general name, and it points to the story of this test, but it doesn't accurately capture what the test is actually testing. What the test is actually testing is that we can add 3 very specific users, Alice, Bob, and Charlie, with particular email addresses, and it's actually only testing a user cap of 3. So if there was a bug, for example, in our Unicode handling, or if there was a bug perhaps triggered by an unusual domain name in an email, we're absolutely not testing for that right now, although we sort of think that we are by the name of the test. So what if we could be explicit about the range of behavior that our test is intended to cover? Basically, we want to generalize from a specific concrete test case into a whole family of possible test cases. That's the core idea of PBT. And computer science has a long history of this idea. This is Barton Miller on the left. In 1988, he gave a university project to some students to basically pipe random data into various Unix utilities, and they found a bunch of crashes doing that. And this is John Hughes on the right. He's the author of QuickCheck, which is a property-based testing library for Haskell and is arguably the most influential form of this idea that was written in the early 2000s. So now I want to show you a property-based version of the user registration test. To do that, we're going to use the Python library Hypothesis, which as far as I know is the most widely used PBT tool in the world. So instead of writing out some specific user data that we're going to register, we want to sample from the space of possible users. And Hypothesis gives us lots of tools for generating random data like this. So here we're defining a custom generator for our user data type. What it does is it first chooses a random name, and it chooses a random email, and it bundles those things together. Notice that Hypothesis has a built-in generator for email addresses. I will come back to that. And here's a complete property-based version of the same test. I hope the text is not too small. I'll just walk through it quickly. So first of all, we generate a random user cap. I've said what the bounds are on the user cap should be. And this gets me thinking about, well, how big can the user cap really be? Then we generate a random set of users of exactly that size. We register them all, make sure that they all successfully got registered, and then we do the same thing of trying a subsequent registration and making sure that that fails. This test is basically better than the test that we started with in every way. It still tells the story. It's just clear about what details are incidental rather than intentional. The only downside is that it's maybe a little bit harder to read because it's a little bit less concrete. And by the way, I'm happy to quibble about the details of this test in the break. There are lots of ways in which it could be improved, but I think you get the idea. One advantage of using a library like Hypothesis is that, opposed to rolling your own random data generation from scratch, these libraries have accrued lots of hard-won techniques for generating data that is likely to crash typical programs. One of those strategies is just to remember to generate duplicate values. This is sort of an obvious one. Duplicate values are unusually likely to cause bugs. Another is to search the syntax tree of your program for literals. If you think about an off-by-one error, for example, maybe you're doing something at the end of a loop incorrectly, there's some boundary of value where that's happening, and it's actually quite likely that that boundary value lives somewhere in your source code. So if you can read the source code and disproportionately choose, for example, the numbers that live in your source code, you're actually more likely to find bugs this way. And another strategy is just to have lots of really good adversarial generators for special case data types. So the email address generator I mentioned is one of these. It'll do all kinds of things to generate email addresses of forms that you didn't think of, email addresses that are likely to cause problems. And some other data types that Hypothesis does really well are floating point numbers, Unicode strings, dates and times. David McKeever, the author of Hypothesis, has told me that some Hypothesis users find that Hypothesis is worth its weight, if only for the Unicode generator. OK, so that's a quick introduction to property-based testing. Now I want to tell you about some experiments that we've done using PBT as a verification layer for LLM written code. All of the examples that I will show you subsequently were done using Opus 4.8, if that matters to you. And I just want to be clear about the status of these experiments. They're very much that. They're experiments. I'm definitely not trying to claim that this is all worked out and that this technique is definitely going to work. It's just I want to show you the approach that I currently think is the most promising for dealing with some of the really quite severe problems that come with agentic coding. Before I get to the specific experiments, think for a moment about the user interface of coding agents. The activity is fundamentally one of writing specifications. You're writing the specifications in natural language. And in fact, programming has always fundamentally been an activity of specification. As soon as we got assemblers and compilers, we stopped instructing the hardware what to do directly. Instead, we say, please give me some machine code that behaves equivalently to this source code. And we don't typically look at the details of the precise instantiation. So the claim that I want to make is that PBT, property-based tests, are a beautiful form of specification for LLMs. They don't suffer from the imprecision of natural language, and yet they don't require the adoption of impossibly heavyweight tools like theorem provers. So another way to frame this is that property-based testing is a sort of high-level programming language for LLMs. The first example I want to show you is an example involving the bin packing problem. The bin packing problem is a well-known optimization problem. The idea is that we've got a set of objects of varying height. So that's on the left. We've got 3 objects of sizes 1, 2, and 3. And we want to find the minimum number of bins of some fixed size that we can pack these objects into. So we've got the solution on the right, where we've packed these things into 2 bins of size 3. This is one of those classic NP-hard problems. It's easy to write a brute force solution for this, but it's hard to write an algorithm that finds a good solution quickly. So here's a prompt I gave to an LLM. I said, please write a solver for the bin packing problem. This will be used in a performance-sensitive context. Please make it run as fast as possible. This is what I got back. Oh, it's an excerpt from what I got back. I'm not gonna make you read the whole thing. But the LLM actually did something really clever. It used a heuristic to write a fast approximation algorithm. You can see this note about the first fit decreasing heuristic. But the thing is that that's not actually what I wanted. I wanted an exact solution to this problem, and it gave me an approximation. Now, to be fair, I was being deliberately vague with my prompt because I suspected that something like this might happen. But I think you get the idea. It would be very easy to omit this kind of detail without thinking about it. Current LLMs are prone to doing this. They tend to fill in missing details from your natural language spec with unstated assumptions. And property-based tests are one way of making your assumptions explicit. Apologies for the excessive Dijkstra quotation. Dijkstra understood this as early as 1978. In that year, one of his articles was titled "On the Foolishness of Natural Language Programming," in which he outlines all of the deficiencies of natural language as a programming interface. So he says, Although changing to communication between machine and man connected in the latter's native tongue would greatly increase the machine's burden, we have to challenge the assumption that this would simplify man's life. So when he's talking about increasing the machine's burden here, he's getting at the hope of natural language specification, namely that we can offload more of our work to the computer. But then he's arguing that despite that, yes, it's true, natural language specs would indeed require more work from the computer, it may not be the case that natural language specs actually make our lives any easier. So, okay, back to the bin packing problem. What would it look like to write a property-based test or a property-based spec for the bin packing problem? Here's one. What this does is it first generates a random bin size, and then it generates a random set of items, and it runs the LLM solution against a reference implementation. So when I repeated this experiment, just augmented with this specification, the LLM did exactly what I wanted. It gave me an exact solution, just one that ran a bit faster than the completely naive one. Now, obviously, this is making a big assumption. This assumes that we have a reference implementation to compare against. Lots of the time, we don't have such a thing. In fact, much of the work of programming is figuring out what the correct behavior should be in the first place. So in that case, we can use what I'll call self-referential properties. So these are properties that relate the behavior of different components of a system to each other, often in the form of algebraic laws or equations without reference to an external model. So one example of a property in this category is the idea of idempotence. This is the idea that if you apply a function twice, it should do the same thing as applying it just once. Maybe you're setting a key to a value in a key value store. Running that operation twice should have the same effect as just running it once. Another very common example is the idea of function inverses. This is that if you think of deserialization and serialization, for example, if you first serialize and then deserialize, you should get back what you started with. So in fact, the second experiment I want to show you involved getting an LLM to write some serialization code for me. This was the prompt. I said, please write a function that serializes the user class, which I'm not going to show, to a string, without using the JSON module. Now, I specifically asked it to not use the JSON module from the Python standard library because I wanted it to do the serialization by hand. This time around, it gave me something completely correct on the first try, which was sort of disappointing at the time because I was hoping to find bugs to show you. But actually, I think this is really interesting because I saw what it popped out. It was some code. It was a small enough code that I could read it, but without reading it, I didn't know whether or not it was correct. Instead of reading the code, what I did is I wrote this test. This generates some random user data. It runs the serialization, and it checks that round tripping is behaving correctly. So I did that, and everything worked out, and it seems like the round tripping is working well. And then I went and I read the code, and I made sure, OK, yes, this does actually look right. And in this case, I think it took me about the same amount of time to write this test as it did to read the code. But I think you can imagine that as problems get bigger, doing something like this might actually be a whole lot easier than reading all of the code involved in the implementation of something. I think this is kind of a deep point, actually. This is because we prefer narrow interfaces where possible. And the property-based test only has to deal with the interface. It only has to deal with the observable behavior of the system and not the messy internals. So especially if you have some nice narrow interface that's hiding a bunch of complexity, this is a really nice thing to do. OK. The third example I want to show you is a little bit different. So far, we've talked about testing LLM-written code with handwritten properties. If we're going to use property-based tests as a specification language for agentic coding, then it really is best if there's a human sort of sitting down, thoughtfully writing out the properties. But I do think it can also be useful sometimes to have the LLM write the properties. Maybe you just don't have time to sit down and carefully work out what the property-based spec should be, and having some LLM-written properties is usually better than having no properties at all. Actually, we found some reasonably high-severity bugs in well-known open-source projects simply by doing this. We just ask an LLM to write some property-based tests, we run them, and we find all kinds of problems. So this is a pull request that got merged a few weeks ago to auto-merge, which is a well-known CRDT library. CRDTs are a family of distributed systems primitives, if you haven't seen them. I don't want to get into the details of like what exactly this bug is. I just want to emphasize that all I did was ask an LLM, hey, please write some properties for this. Please run the obvious properties. And it's spewed out a really quite gnarly bug that was very deep in the internals of the system. This is showing one of the nice things about property-based testing, which is that you don't have to have complicated properties to find complicated bugs. And tests like this are almost pure upside. I don't want to say they're completely pure upside, because of course they are code that gets maybe checked into your repository, and that does introduce some burden. But the worst thing that can happen is that we spend some time investigating a violation of a property that turns out didn't need to be true in the first place, and clarifying our understanding of the spec. Okay. Before I wrap up, the last thing I want to do is introduce you to one of the most exciting ideas to come from this world, which is the idea of shrinking. Take a look at this test. This is a deliberately failing test for the purposes of illustration. The idea is that we're sampling random lists of integers, and then we're asserting that the list should never contain a sequence of 3 equal consecutive elements. Now, of course, this is not true in general. There do exist lists that contain 3 consecutive equal elements. But the thing that I want you to notice is what happens when we run this test. This is what an excerpt of the output looks like. The thing down here at the bottom is the specific counterexample that was found. So it's given us the list 0, 0, 0. Now, this is kind of amazing, because actually, that's the smallest possible counterexample for this property. And I did no work myself to make sure that we got a small example. If you think about the chances of finding this example by pure random sampling, they're really quite low. So Hypothesis has lots of machinery that will do this sort of test case reduction for you without requiring any work on your behalf. And this is just amazingly useful when it comes to debugging, because it means that you often have a simple example to look at. The claim, well, the hypothesis I want to propose is that shrinking becomes even higher leverage now that we have LLMs, because we can take shrunk test case output and we can feed that back into the LLM loop. So this is totally anecdotal, but it's my experience that LLMs benefit roughly as much from shrinking as humans do. I don't have any concrete examples of this to show you, because all of the examples I've seen this have been on projects at work that I can't talk about, but I hope you get the idea. I want to make an admission. All of these were cases where executable specifications were relatively easy to express. Lots of software is much messier than this, and I think it's kind of an open question how we grow these techniques to handle all the messiness of the real world, and that's part of what we're working on at Antithesis. That's all I have for today. Happy to take questions, and happy to hear from you by email.
Thanks, very interesting talk. Do you have any heuristic for assessing how good of a coverage you have in terms of properties being tested for a function or whatever you're testing?
Yeah, great question. I think basically the answer is that we don't have any better heuristics than we already have for unit tests. I mean, people use code coverage. You can look and see what proportion of your code base is being exercised. But in terms of thinking at the level of properties, I don't think we have any good answers. In fact, I think one of the difficult things about getting into property-based testing is that it takes a while to develop some intuition for what properties your system should have. And yeah, I think it's kind of an open question how we start to teach people that intuition.
Thank you for that talk. That was really interesting. As well as shrinking, what are other kind of mental models or approaches you might take to reconcile like the cost to benefit of running property-based tests, for example, in like a CI context? I've experienced sort of a little bit of pain where developing property-based tests, it takes a lot of time, like you say, to develop the properties, but then the more that you add, we often come up against constraints in that they slow down the entire CI pipeline when you get to a certain head count. So have you had that trouble? What kind of mental models do you?
That's interesting. The way that we do it is that we typically break our tests into tests that are run as part of the development cycle. So these are tests that you'll run locally on every commit, and those should happen really fast. So by default, Hypothesis will run 100 test cases for every property. That's a low enough number that unless you're testing something heinously slow, that should really happen instantly. And then we also have sort of nightly runs that do long-running fuzzing or property-based testing. We call them campaigns. So these are things that we'll spin up overnight, and we'll just say, run as long as you want, run until you find something, keep going even if you do find something. But those we're not waiting on those to push commits. Yeah.
Tricky question, maybe. Should we be trusting the AI agents to know when and if property-based testing is the appropriate technique to be using, and what the properties should be? So in a sense, should the takeaway be a simple thing in your prompt to say, use property-based testing if appropriate, full stop?
Yeah.
And let it make all the judgments. And if the answer is no to that, then how can the AI ever end up knowing that the answers to those questions? How do we shift the needle, or is AI baking in a point of view on the world where it doesn't know these high-quality techniques?
Yeah, great.
And we'll never learn them.
Great question. I think it should be our mission to, everyone here should go out and do property-based testing so that the models get trained on this, and then they all just start doing it by default. I think this is kind of a fundamental question. My preference is really that you need to start with a trusted base somewhere. And I think that the human beings should be the ones that are doing the specification. So it's really my preference that humans write the properties and LLMs write the code. Now, I put this other stuff in about LLMs writing properties because that's just not practical for a lot of people. I think my current recommendation is that if you're comfortable with property-based testing, then you should write the properties. But if you're new to this and you're not sure what properties to write, then it's definitely a helpful aid to have some properties proposed to you by the model. Does that make some sense?
Hi, thanks for the talk. So all this is quite small scale. All the property-based testing stuff is all, whenever I see it, it's always in the small. How does this kind of relate? Do you use these techniques on a wider scale with your Antithesis platform?
Yeah, absolutely. That's really the big difference with Antithesis. Is with Antithesis, we're doing sort of simulation of your whole system. You give us your whole system packaged up into our environment, and we really try to run the whole thing in as close to a real-world environment as possible. That's a much slower, heavyweight sort of industrial process than this. I think it's really valuable to do the longer-running, big system fuzzing in addition to the sort of small component-based, property-based tests like this. It's just that the component-based sort of individual function-level stuff is an easier context to introduce people to the ideas with.
Thank you.
Great. Thank you all.